Hello and welcome. In today's video, we're going to have a look at matrix inverses. Now, unlike Gaussian elimination, matrix inverses are something that we might actually use in a programming situation. If we have a transformation, an inverse of a transformation, we'll do the opposite. These are sometimes useful. What is an inverse? Well, let's say we have I'll go through the definition. So say we have a matrix A. If there is another matrix which has the property that it doesn't matter which way we multiply it, but whatever way we multiply it, we get back to the identity, then that unknown matrix is called the inverse. Now, in the previous video, we had a look at Gaussian elimination, and Gaussian elimination is a pretty good general way to solve for a matrix inverse. If we're doing a 2 by 2, yeah, there are formulae for it, but for a larger system, Gaussian elimination. So the way this works is we look at, in Gaussian elimination, typically we had this sort of thing. So we had a matrix A times an unknown vector produced an unknown vector. Now for matrix inverse, we have a matrix A times a matrix X produces the identity. And then we do all this work and we get it to the form where we have the identity on the left-hand side. Instead of A, we reduce that. Instead of row echelon form, we get it into just a regular identity matrix. And then what we have on the right-hand side has to be the inverse, if that makes sense, because X doesn't go anywhere. So we know that X is, anyway, it's a bit of trickery, but when we actually get into the swing of it, it's pretty cool. So I'll go through some examples. These are going to be the same matrices that I did in the previous video. We're just going to get their inverses. And remember the cases. So this matrix here corresponded to the case of having a unique solution. So again, I write this out, and on the right-hand side, instead of augmenting a vector, I augment the identity matrix. Okay, so we can almost go through exactly the same processes as we did in the last video, because we're reducing the same matrix. Okay, and the bit to really pay attention to is we need to do this to the rows of the right-hand side as well. So here we have row 2 minus 2 times row 1. So if I take 2 times row 1, it's just putting a 2 in this first component here. So there we have it. And then down here, it's, oh yeah, that should be a minus 2. Minus 4 times row 1. So it almost looks like we're sort of tracking the history of the operations that we took. Okay, so the next thing we do is we want to zero out here. So we say okay, so we got that. Now this was, what was it? 3 times row 3, then subtract row 2. So we go through here, the first 2 rows are unaffected. And then the last row, we have negative 12 minus negative 2 is negative 10. And then 0 minus 1, and then 3 times that, so 3. Okay, cool. But remember, we want to get the identity on the left-hand side. So now we take the diagonal and we cancel everything up above. So we can say row 1, now we're going to go multiple of 2 and 3 is 6, so we'll say 3 row 1 plus 2 row 2. I'm messing this up. Okay, so go through here. We have 3 plus, okay, just double checking my math from the step before. Okay, so 3 plus negative 4 is negative 1. Then we have 0 plus 2. Okay. Okay, great. Now again, we want to take this column and cancel everything up above. And this is where we sort of get into some not fun times. So multiples of 7, 5, and 4. I can't think of any common factors, so I'll just have to multiply them all. That's, let's see, 35 times 4 is 70 times 2 is 140. Okay, so I'm going to say row 1 will be 20 row 1 minus 140. That's 35 row 3. And then row 2 will be 28 row 2 minus, 35. It's not fun. Look, we have computers for a reason. Anyway, where was I? Okay, so where was I? So we have negative 20. So negative 20 plus 350, which is 330. And then we have negative 40 plus 35. It's negative 5. And then we have 0. 0 take 105. And then, okay, 28 times 3 is 84. And then this is, that cancels out. And then negative 56, so plus 350. And then 28 plus 35. And yes, I am using a calculator because life's too short for this stuff. Okay. And then, we're going to take 105 again. And then the last row just stays the same. So we have 0, 0, negative 4. Okay, so we're almost done. In order to get the inverse, we would need these rows to be 1s. And so what we can do is we can divide the corresponding rows with each of these coefficients. So I'm just going to leave it in big nasty form for now, just to get the question done. So we take every element here and divide it by 60. And then in the second row, we take every element divided by 84. And then in the third row, take every element divided by negative 4. A little messy. Honestly, could be worse. And there's our result. So this is a fun exercise if you've got a lot of time on your hands. When I was a student back in the day, I used to love sitting in the library and just doing these all day. It was so much fun. I wonder if it ever got me anywhere, but here we have it. That's how you do a matrix inverse. Let's go through another example. Okay. This corresponds to the matrix in the last video, which that system did not have a solution. So let's see what the inverse looks like. See if we have any more luck with that. So we'll go through the same steps as before. Okay, and then we can say, alrighty, to cancel out, row 3 will be 2 times row 3 plus 3 times row 2. So we have, what do we have? This is -6 plus 6, that zeroes out. And then we have 0 plus 3, 2. Okay, so we have a problem. If we look at this, each of these, the full row and a column is an equation. So this equation is actually consistent, this bit. This is fine. It is this equation here, which is a problem, and this equation here, because it's not possible to add 0 times a bunch of things and get 3. It's not possible to add 0 times a bunch of things and get 2. So we can say no inverse exists for this matrix up here. Okay, let's have a look at one last example. And yeah, again, I'm going to be using the same one as the video before. So this is the matrix which had infinite solutions. Okay, so we'll go through the same steps. We'll say row 3 equals row 3 minus 2 row 1. Okay, and then row 3 is row 3 plus row 2, not row 1. Okay. So yeah, we get a similar case to the example before. In the third row, all of these columns here make an inconsistent equation. So again, no inverse exists. Okay, so summing everything up so far. In the previous video, we looked at Gaussian elimination, and we looked at cases where we had a unique solution, infinite solutions, or no solution at all. In this video, we looked at inverses, and inverses are a tool that we can use to solve systems of equations, and inverses can be calculated with Gaussian elimination is a good method to do it. But we also saw that in some cases no inverse exists. So I wonder if there's a way that we can determine whether or not an inverse exists. And there is. It's the determinant, and it's in the next video. All right, see ya.